Here's our agenda for Wednesday, October 28th. 1. We will review the discussion question from Tuesday. 2. We will review calculating net force practice problems, also from Tuesday. And 3. We will analyze motion graphs. After this video, you need to complete the discussion question found in your Schoology folder, and then also be sure to fill in the attendance link. That way you are counted as being present. First up today, we're going to be reviewing the discussion question from yesterday. It reads, a hobbyist collected data about the motion of a toy train on a straight track and then recorded the data in the graph below. Which of these accurately describes the motion of the train? Let's start by looking at our X and Y axis. The X-axis is given time in seconds. The Y-axis has distance from the starting point, and that's going to be in meters. So we need to start by analyzing our graph. Looking at time 0 through time 2, the slope of our motion is going to be the same, meaning we have constant speed for this first section of the graph. So our train is not speeding up or slowing down, it's moving at the same rate. But between times 2 and time 3 on the graph, we have a bit of a curve, which means our train is beginning to decelerate or slow down. After that, from time 4 onward, the position of the train has not changed. It's staying at 6 meters. Meaning that time is continuing, but our train is not moving. It's staying at 6 meters away from the starting point. That means our answer is going to be letter C. The toy train moves forward at a constant speed, slows down, and then stops. The first part, from 0 to 2, is the train moving at a constant speed. Then we have it slowing down. And then the rest of the graph shows that it is stopped. Now let's review the calculating net force practice problems. These were not for a grade, but they are good practice. This first one has 2 forces acting on an object. The first in blue is going to the left with 5 newtons of force. The second is in red and it's going to the right with 15 newtons of force. Because the 2 forces are acting in opposite directions, we're going to be subtracting them. So 15 newtons minus 5 newtons means our answer is 10 newtons, and it's going to be moving towards the right in the direction of the larger force. On this problem, we have 3 different forces acting on the object. 2 of them in blue are going in the same direction. The third in red is going a different direction. To begin, we need to add the 2 forces that are going in the same direction. So 3 newtons plus 2 newtons is going to give us 5 newtons of force going up. And we need to subtract the 2 newtons of force that are going down. So 5 newtons minus 2 newtons means our net force is 3 newtons, and our direction of motion is going to be up. On this problem, we just have 2 forces, both 4 newtons, and they're both moving towards the right. When we have 2 forces going the same direction, we want to add them. So 4 newtons plus 4 newtons means our net force is 8 newtons, and it's going to be moving towards the right. On this problem, we have 3 forces, a 6 Newton force pulling to the left, and then 2 3 Newton forces both pulling towards the right. We need to start by adding the 2 forces that are going in the same direction together. So that means we have 6 newtons of force moving towards the right and 6 newtons of force moving towards the left. We then subtract our 2 forces, so 6 newtons minus 6 newtons is our net force of 0 newtons. And when we have 0 newtons, we have balance forces, so there's no change in the object's motion. On this last problem, we have forces pulling in 4 different directions. We can start by canceling out the 2 2 Newton forces. The 2 Newton forces are both pulling in opposite directions. So 2 newtons minus 2 newtons means we have 0 newtons of force going in the left and right direction. So we can go ahead and cross those off. That means the only forces left acting on this object is the 1 Newton force pulling up and the 4 Newton force pulling down. In order to find our net force, we subtract. So 4 newtons minus 1 newton means our net force is 3 newtons, and the object is going to be moving downwards. Now we're going to analyze a motion graph. To begin, I'm going to break this motion graph down into 4 separate parts. From 0 to 2 seconds is going to be part A. From 2 seconds to 5 seconds will be part B. 5 seconds to 7 seconds is part C. And then from 7 seconds onward will be part D. Let's begin with analyzing part A on the motion graph. Part A goes from 0 to 2 seconds, and we can see that there's a straight line. That means that we are traveling away from the starting point at a constant speed. On part B with the motion graph, part B has a steeper slope than part A, but it's still a straight line. That means we're still moving at a constant speed, but it's a faster speed than what we were traveling at originally. On part C, which goes from time 5 seconds to time 7 seconds, our distance from our starting place is 25. It does not change from 25 meters for the entire duration of letter C. That means that our object has completely stopped moving. Its distance is not changing. On part D of the motion graph, we can see that the object is now starting to travel back down towards 0. 0 is our starting place, meaning we are now traveling backwards, but we're going at it at a constant speed. If it was not constant speed, our motion graph would actually have a curve to it, like that or like that. So a straight line on a motion graph means that we have constant speed. If you see a curved line, it means we are not traveling at a constant speed. We are speeding up or slowing down. Here's another type of motion graph, which shows the relationship between time and speed. Time here is measured in minutes, and speed is given in meters per second. This first part of the motion graph is a straight line, which means our speed is remaining the same. So this is showing constant speed, which means if we have a constant speed, all of our forces are balanced. So our speed is not changing. We can say here that maybe the car is going 10 meters per second. Okay, the second part of our motion graph is the center right here, and it's a upward diagonal. This means that we have an increase of speed, so our object is speeding up. So we have a change in speed here, or acceleration. So in this area, in the middle of the graph, we have unbalanced forces. The third part of the graph is flattened out here towards the end. This means our speed is not changing. We're still moving, we're just moving at a constant speed. We can go ahead and say that perhaps this object is moving at 20 meters per second. It's a constant speed, so we have no acceleration. So reviewing one more time, the first part of the graph that is flat has constant speed, so the object is moving, but it's moving at the same rate. So maybe it's 10 meters per second, 20 meters per second, 30 meters per second. It's not changing, it's not speeding up or slowing down, it's remaining the same. So our forces are balanced. In the second part of the graph, we have a diagonal line, which means we are speeding up, so we are accelerating. In this area, we have unbalanced forces. Finally, the graph flattens out again, This means that we are moving at a constant speed. So we don't know what that is. It could be 50 meters per second. It's just at a constant rate. So we have balanced forces here as well. Here's the last graph that we are going to analyze today. Again, it's set up that time is on the x-axis and speed is on the y-axis. In the first part of our graph, we're starting towards the top. Let's go ahead and say that this is 10 meters per second. In this area, we're going from high to down towards about the middle of the graph, and then it levels off. This means that we're actually slowing down. We can say that maybe we went from 10 meters per second down to about 5 meters per second. In the middle part of the graph, it's leveled off. That means we're not changing our speed. We're remaining at a constant 5 meters per second for a couple of minutes. So again, we're not stopped. We're just moving at a same speed or the same rate. In the third part of our graph, we're continuing down from 5 meters per second towards the bottom of the graph, which is going to be 0 meters per second. So here we are also slowing down or decelerating. And then finally, when we stop, we will have no motion. Looking at how forces would be affected, slowing down would be unbalanced because we have a change in our speed. When we're traveling at the same speed, this means that our forces are balanced, that there's no change. And then again, speeding up or slowing down at the bottom, we're going to have unbalanced forces.